All right, so it's time to get started, and I will start by saying sorry for putting your homework up late. I put a couple of assignments up for you, but you have a week and a half or more to work on them. And the first one is a regular assignment focused on unique printing processes, so things that you're interested in. That's a relatively open assignment, so it'll give you an opportunity to look into stuff that you want to look into. And then the second assignment is short, but it will take some thinking because what I'm interested in is what are your thoughts about your final project paper presentation? And so if you look in the syllabus, the parameters of the final paper and presentation are in there, and we can talk more about that as needed. But I figured it was worthwhile to start to think about what you might want to look into, think about how what you've learned in this class relates to your own interests, and of course, the strategy for those of you that are writing papers or working on additive manufacturing for your thesis research. This could be a component of your literature review, or they'll give you the opportunity to learn a couple things that you need to learn. And so I want to make sure that the project is useful to you. And so that includes learning something that you're interested in, but also perhaps being able to take this assignment and expand on it for your thesis. So those are up on Canvas. And of course, if you'd like to have office hours, or if you have any questions, or if you'd like to just dialogue some ideas, including, trying to find enough resources in the open literature to complete your project, just shoot me an email. We can have a Zoom office hours, or we can go back and forth by email corresponding like that. So anyway, it's time to start thinking about these things. And so I want to make sure that this is on your radar screen. So before we get started on the slides, are there any questions from anyone, any comments, anything that folks want to say before we get started with lecture?
I have a question. I'm not sure we already talked about this, but when you were explaining about in material extrusion that you have maybe like two nozzles, one for like each material, or one for like the support structures and one for the main material, where is it that you tell,
so
like where is it that you tell the file, like this is this material, this parts are this material, and this parts are this material? Like, is that in the STL file, or like where do you specify, I guess, like that difference?
Yeah, so I only caught part of that, Paula, but it's either my internet is not great or Zoom is not great. But so when you specify a multi-material structure, you can specify different materials in the STL. And so usually that generates two different models for Cura that you merge. And so you can identify the material either in the 3D printing software, or if you have two models and you merge them, you can identify the different material in Cura. And then in Cura, which is going to be your slicing software, that's where you tell the printer what material is what and which nozzles are going to print which material. So Cura, which is the slicing software, and Cura generates the G code or the instructions for the printer. That's where you say, I'm going to use ABS for this part, and I'm going to use PLA for this section of the model, and then here are the parameters for all that. So I don't know if the printers you've used have used Cura, but you tend to define the different materials when you slice it and when you make the tool path, because the printer has to know what materials are where in order to set up the right machine parameters. And that's done a little bit differently depending on what you're slicing and what your G-code generation software is.
Okay, yeah, that makes sense. Thank you.
Yeah, if anyone has hands-on questions about how to set up prints or how printers are used, or if you have an Ultimaker and you're interested in something, or if you have a custom printer, there are some people in class that have a lot of experience with setting up prints, going from SolidWorks or AutoCAD Inventor or something like that, or even Fusion 360, to importing those STL files into something like Cura, which is a slicing software, and generating G code, which is the machine movement or machine instruction program or list of instructions. And those things are covered in other 3D printing courses that we have. So we don't go through a lot of the nuts and bolts of the different software and 3D modeling and how you define different materials within your model. That's covered in other classes. But if you've got pressing questions, I'd be happy to chat about it, or there's a lot of resources on campus that I can help direct you to if you're really stuck on a 3D printing question that you can't figure out how to solve. So we'd be happy to chat about that anytime.
Okay, thank you.
Any other questions or comments from the class before we get going here? Okay, so take a look at the homework. I got it uploaded later than I'd like, but I gave you, I think, enough days. And of course, if anyone needs 1 or 2 extra days, because life happens, I certainly understand that at this point in the semester. So take a look at Canvas. Make sure you get an early start on what you're interested in, and shoot me any questions that you have. So we're going to be talking about SLA and SLA materials for the next couple of lectures. And so stereolithography, by its nature, involves some polymer chemistry. So we're going to talk some chemistry, but the chemistry is really there to help you understand how the material is working and what some of the issues are as we start to interface printing technology with materials technology, with trying to get the parts that we're interested in. So you'll have to bear with some of the organic chemistry, and this is a messy slide, but just to remind you that in general, all of the 3D printing resins that we talk about are going to be UV activated acrylate photopolymers, and we're talking about liquid to solid transitions that happen very quickly in the SLA process. And so every single resin that we're going to talk about and every single resin that you can buy works on exactly this principle. And it's the details of the resin chemistry give you all the different SLA materials out there, and eventually composites, because these also serve as the binder for whatever composites we're interested in. And so there's a lot of guides out there. And so if this comes up online here in a second, it looks like my Zoom is going very slowly. If you can't hear me or if something's going on with the audio, just warn in chat. I'm taking a look at it. But anyway, the slides will come slowly here. They're different from what I'm seeing. Let's see it. There we go. So there's a lot of guides out there to help you select different stereolithography resins. And those guides in general are based on properties. And so when you look at slide 28 in this SLA Lec 8, you can see that a lot of the SLA resins, in this case, the ones 3D system cells, have all the tensile moduli, flexural strength, the hardnesses, the impact, the heat deflection temperature. That's all listed, and they try and give you an idea based on the resin name what some of the properties are. Is it high impact? You know, what color is it? Is it high temperature, like this Acura Bluestone here? Is it just a standard resin? So white standard resin that's ABS light. Oh, hold on. Okay, it's still working. I think my Zoom on my computer just died. But anyway, again, if we run afoul what's going on online here, just let me know. Hold on. So all of these resins on these two pages, slide 28 and 29 in lecture 8, are all based on acrylate photopolymers. And it's the mixture of oligomers and monomers and other chemistry in the resin that give it the properties that are desired. All right, hold on. I'm rearranging my Zoom on my computer so I can see what's going on. So we briefly touched on cyanoacrylate. So we're going to talk about that in a second. And really this idea of post-curing, or what we do to the SLA part after we do the acrylate photopolymerization, is something that's interesting to making finished parts that are not prototyping parts, don't have high enough strength, but to produce finished, in this case, automotive grade or electronic grade materials, which is what cyanoacrylates are used for. That's of interest to people with SLA. Hold on, let me get my chat going here. Sorry for the technical difficulties. Things are going so smoothly at the start of the semester. All right, are my slides sharing? Can people see my slide share? You can unmute yourself and just let me know in the chat. But can you see these slides?
Yeah, it's good.
Yeah.
Okay, yeah, I can't, something's wrong with Zoom on my computer, but if slides disappear, let me know. So we'll talk about what's going on specifically with this chemistry further in the lecture. So we're gonna leave lecture 8 and we'll go to lecture 8.1. Will come up here in a second. All right. And so we were getting into this last time and we watched a couple videos. And so a couple of these will look familiar to you. But in general, we're talking about thermosetting polymers. Now, whether it's the cross-linking is done in photopolymerization or we do a thermal post-processing of the resin, that depends on exactly what chemistry we're interested in. And the problem with thermosets is that they tend not to have as high a strain to break as thermoplastics. And so if you're interested in a high strength epoxy, or if you're interested in a high strength cyanate ester, or if you're interested in a thermally cured silicone, it's a little bit more difficult to have these long elongation properties or to have high toughness versus some of the thermoplastics. But whether you choose a thermoset or thermoplastic depends on a lot of things. You know, what's the temperature range? What application are you interested in? What processing equipment do you have on hand? What's used in the industry? And so material selection is very dependent on exactly what's going on in terms of the specific part, the specific use. And so it's hard to say like all automotive plastics are going to be thermoplastics, or we need to use thermosets for everything. But this material selection, whether you choose a thermoset or a thermoplastic, will depend certainly on a lot of things. So, but this gives you a general guide. And so in this process of going from a liquid to a solid, that process is called gelation. So the specific science that we're interested in, or the specific physics that we're interested in, is this relation physics of these thermosetting polymers. And so you can see the schematics here. My computer is just having a tough time today. You can see the specific schematics here show exactly what's happening when you go from a mixture of monomers and oligomers. Because in general, oligomers are just big monomers, or they're very small polymers, but they're still liquid-like, and they can be liquid and viscous. And then as we start the reaction, we have polymerization. And you see here in this diagram, we still have mostly isolated oligomers. So this is mostly isolated oligomers. And, oh geez, my Zoom on my computer is really having issues. Anyway, if you can still hear me, let me know. Otherwise, you know, if I fade out, send me an email or something, but my computer is not doing well here. But anyway, hopefully my iPad will make it through the lecture. So I'm just going to keep lecturing, and we'll see how this goes. But please speak up if something goes wrong. But when you have mostly isolated oligomers, this can still flow. But it's very viscous. And right at the point where you complete long-range network, this is gelation. And where the material can't flow anymore, we go from a viscous liquid to a gel state, and then finally you have full curing. And so this gives you a good schematic about how this process works, but finding the gel point is a matter of experimenting, and how to find this transition from a viscous liquid to a solid gel is a matter of mechanical properties. And I'll show you how that's done in the next couple of slides. So you see in D here, we have this completed network, even though this is a little bit different diagram than what we saw before. But now that you have this fully extended network, you have a gel. So again, we're going from liquid, viscous liquid, to gel. And we might have something like a very viscous liquid. And then we have a gel, which is, of course, a solid.
I have a quick question.
Go ahead.
Is this happening during printing, or is this like for the resin before printing? I'm just a little confused.
So this happens when the light is on. So this happens quickly during the photopolymerization. And so this last step, where you go to a gel, So let's say A, B, and C all happen quickly when light is on. So this happens within 50 to 100 milliseconds. So these polymerizations are really fast because you need to get a solid part when you print a layer before you move on to the next layer, or else you can't release the tray, you can't pull up the solid part. And then the last little bit of cross-linking where you get full curing, that can happen later. So that's not as important to get to that perfect solid until you need the high mechanical properties, until you need something else. And so you just need to get the material to go from a liquid to a solid, even if it's a little bit of a soft solid, or that's where gel comes from, right? It's a little bit of a soft solid like Jello, but you can still pull it up during the printing process, if that makes sense.
Yes, thank you.
Okay, good. Yeah. So
I have a question as well, really quick, and it's kind of to what
Go.
she was talking, but I'm not. Would there be any case where this would happen on its own without being exposed to light, where you have an unstable resin?
yes. So if your resin is unstable, or if you have a lot of light bleed, or if you leave your resin in a clear jar and it cures on its own, this can certainly happen in an undesirable fashion because in order to get these reactions to happen quickly, you need very reactive monomers. You need to have very active photoinitiators. And so it's a big challenge to make a resin that prints fast, but is still stable.
Okay, makes sense.
Yeah. So when you get low resolution prints, or you get light bleeding, or you get resin curing in your material, or resin curing in the bottle, this exact reaction is happening, just the resin's too sensitive. So if you make a resin that's too reactive, you have uncontrolled reactions, because any reaction that happens using photochemistry in general can also occur thermally. So in some cases, if you have a resin, photocuring resin, and it gets hot, that's an issue. It will cure as well. And so finding the right balance between reactivity and curing is really important.
Okay, thank you.
All right. So any other questions? I can't see this for some reason on my computer. It's just having major issues, but I can definitely hear the questions mostly. And so I'm not going to be able to see the chat. So please just unmute yourself and ask a question if there's anything else. Anything else people want to discuss on this slide? Okay, so a lot of times you'll hear curing, you'll hear gelation once in a while, but the polymer physics process here is gelation, and that's what we're interested in. And gelation is a scientifically defined principle, and so we can find science that helps us figure out what's going on at gelation. And so whether or not we start with the Newtonian liquid, that depends on exactly what type of mixture we have. But we see that the viscosity here, so eta 0 is the viscosity, rapidly increases as we undergo polymerization. And only liquids have viscosities. And so eta 0 is just the zero shear viscosity. And so we polymerize that liquid, the viscosity increases rapidly. And then at the gel point, or the conversion at the gel point, we have this first appearance of moduli, because solids have moduli. So this is where we need to get to in this rapid curing before we can pull the part up, let resin flow in, and print the next layer, depending on how printing process is going. And so in order to find this gel point, lots of times people will construct a working curve, or they'll look at the tackiness of the resin, or there's other ways to find this gel point. And we'll talk about that analysis as we talk about different resins. But this is what people are really interested in terms of how to get to this gel point. What's the dose of light? What's the polymer chemistry? How much crosslinker do I need to add in order to get to this gel point so I can do my 3D printing? So this is displayed in various ways. And so whether it's complex viscosity, which is the eta star, or it's a zero shear viscosity, which is a liquid or a modulus, you know, this reaction time can be 50 milliseconds to 200 milliseconds for SLA. And of course, it has to be fast because in order to get fast printing, like in a carbon resin, you really need this cross-linking process to occur quickly because you're continuously pulling up the part. And so you need to be building new solid material at the bottom of the part right above the dead zone, as we saw in previous videos. And so this is just showing again how these working curves occur. And even though this is slow, so this is an epoxy, so this is natural log of time in minutes, so that's a long time. And this is an epoxy amine cure, which is a thermoset at different temperatures. You can see that as we increase temperature or as we increase the dose of light, as I'll show in some of the working curve examples, you can increase the speed of the reaction so you can process the material faster and faster. So this gives now some idea about how these materials are processed and some of the parameters that you need to undergo this liquid to solid transition. And then we're going to talk about how you get the properties that you need in a specific part. Any questions so far?
Dr. Hickner.
Yep.
On the previous slide, could you go over what the N naught or N star was?
So N star is just another measure of viscosity. This is called the complex viscosity. And it's just a way to bridge. Sometimes this is eta naught. So that's called the zero shear viscosity. And that's really only defined for liquids. And so the complex viscosity is a way to plot liquids and solids together. And you can look up the mathematical definition of eta star. I actually don't know it off the top of my head, but modulus G, so G prime and G double prime is the storage and loss moduli. And they're defined for solids. So this is all under the banner of liquid and solid rheology. And these different quantities, eta naught, eta star, and G and G prime are just different ways of expressing the flow properties or the stiffness of the material, if that makes sense.
Yep, thank you.
Okay, yeah, and you can look up the mathematical definition and how to measure these quantities in something like a polymer physics textbook, or we certainly have classes on this, but this is enough to get you started understanding how the viscosity and modulus of these materials change as we do 3D printing on them. Okay. The other thing that's interesting in this plot right here is that they're plotting the glass transition temperature of a thermoset. That's fine. So you can measure the TG, and you notice that the TG, or the plateau, TG increases as curing temperature increases. So if you want a high temperature material, you need to cure it at high temperatures. And of course, we know that all of the acrylate photopolymers that we've talked about so far, they're generally around room temperature. And so you'll see a lot of the cyanate ester chemistry that we talk about will be a higher temperature cure. And so we'll talk about that when we get to those chemistry slides in a second. I'll pause here. Any questions? All right. Again, I can't see the chat, and I can't see the slides because my computer decided not to Zoom today. And so just butt in, please, if something pops up. So there's a lot of cool examples of SLA parts and prototypes and materials online. We won't go through all of them. I just wanted to provide some slides and some links here, but this is really a way that you can produce, using SLA, a way that you can produce parts that look like production quality parts without having to injection mold or something like that. So there's a lot of examples. You can check this out, and we'll talk about a couple of chemistry examples and a couple of key applications further on in the class, but this just gives you a frame of reference. One of the interesting things that you can do with SLA that we haven't talked about is SLA can give clear materials. So that's interesting. This is really hard to do with FDM or SLS, and so you can get clear parts. And so now those start to look like showpieces. So, and there's a lot of different guides out there again. So if you're interested in looking up what's going on at 3D Hubs, there's a lot of standard prototyping, general use resins. Engineering resins tend to have high strength and toughness. We'll talk about those for end use. Applications. Dental and medical resins, these need to be biocompatible. And so they need to have low leaching. They need to be non-toxic, biocompatible, non-toxic. And they usually need to be registered or certified by the FDA. We'll talk about that process a little bit. And then castable resins are cool. I show an example of this further on. These can be used for metal casting to make jewelry or to make prototype molds for casting other types of metals. And so that's interesting because if you've ever taken a metals lab in school, in general, you make a polystyrene or foam sculpted shape. And then you take that foam shape and you bury it in sand or plaster and then make an investment mold out of that and then pour the hot metal in. But now with these castable SLA resins, you can do some really interesting and intricate casting at small scale with your 3D printer. Any questions so far? All right, so this is just one example right here, and this is to make a really clear SLA, or to make the lens in this camera. But what's cool about this picture right here is all parts were made with SLA. So that's interesting. Everything from the lens to the dials to the body of the camera is all SLA, because of course this is Formlabs, and that's what they do. And so the key for clear materials is that they don't just come out of the printer clear. There's a lot of finishing that needs to be done. And so everything that comes out of an SLA printer has a little bit of a frost on it, because you can't get perfectly smooth surfaces with SLA, because you can only get about 25 or 50 micron resolution at the best. But if you polish the samples in general, they're pretty dense on the inside because the layers are well integrated. So if you break open an FDM part, we know that it's not clear inside an FDM part or a material extrusion part, because there's gaps in between the roads. And those air gaps, or any roughness internal to the part, is what causes the material to be translucent or hazy all the way through. So even though we might use a polycarbonate feedstock in material extrusion AM, we can never get a material extrusion AM part that's perfectly clear, even if we polish the surface, because of the internal porosity, which scatters light. But because SLA parts have good layer integration, so SLA parts don't have internal voids, they can be polished, their surfaces can be manipulated, and you can get relatively clear parts depending on the exact resin composition and how well it was cured. So they walk you through this in the Formlabs how-to section in one of their application notes. And the other thing that they do is they coat. So you can coat rough surface to get smoothing. Now, this is different than solvent smoothing material extrusion AM parts. So if you've ever done a lot of material extrusion AM with PLA, there's a technique called solvent smoothing. It's not really used industrially, but it's used by the hobbyists, where the solvent penetrates the thermoplastic and sort of melts it a little bit and smooths it, because of the inclusion of solvent in a polymer makes it soft, and so you get this coating. You can't do solvent smoothing with SLA parts because they don't get softer when you impregnate them with solvent, but you can, in essence, this is like putting nail polish on, or putting a finished polyurethane coat on a stained table. It starts to look smoother because of this smoothing clear coat that you put on top. And so this is one of the techniques that Formlabs talks about in this application note to get really smooth and transparent structures and to even out the inherent surface roughness in the process. So you might go from something like 50 micron surface roughness. And they didn't measure it in this application note, but this thing is going to have like 2 micron or less than 2 micron surface roughness. And we've talked a little bit before how to measure surface roughness in 3D printed parts, either using optical profilometry or stylus profilometry or another roughness measurement technique. But things that are starting to look smooth and smooth like glass generally are micron or submicron surface roughness. And things that look a little hazy and have a little texture to them are on the order of 50 micron plus surface roughness. So you can sort of get a qualitative evaluation of the surface roughness of these parts. Any questions? Okay, hopefully you can still all hear me. I think my Zoom is working on my iPad, and so we'll keep pushing on here. So we've talked a lot about additive manufacture of materials that you might want to use in your application. One thing that we haven't talked a lot about, other than in injection molding, is to additively manufacture the mold and then use that to produce the part that you want. And so Formlabs has a nice application note on 3D printing vacuum forming molds for chocolate. And you know, this is a Valentine's Day themed picture right here, but you all know that Halloween is coming up, and so we're all going to be at home eating our candy instead of going out this year. But Hershey has started to use this process now, not to additively manufacture the chocolate, but to additively manufacture custom molds for casting chocolate. So that's very interesting, is that you make an SLA tool, and you can't cast chocolate in SLA material because it's not food grade SLA. So this SLA tool is not food grade or certified for food contact. So this is the FDA again, you just can't do whatever you want. And so you actually can't cast chocolate in that SLA mold. But this is food grade vacuum formed you can make a bunch of vacuum formed molds from that, and then you're off and running on casting whatever you're interested in. And so you can make custom food this way. You can do lots of interesting things. And so it's one of the techniques, rather than making the product that you want to sell, it's helping to make the tool that makes the product. So this is always an option. This is worthwhile remembering as you think about how you're going to SLA something, or how you're going to 3D print something, and whether you want to 3D print your product or print tools. All right, I'm going to switch over to Zoom for a sec, and it looks like things get out of read the application. But we talked about metal casting, and this is really cool. So these are SLA castable resins. And so now these resins are specifically made to integrate into casting. This is for metal. I think this is platinum casting, where they show the shape that's made in SLA, and you bury this in plaster, and then you do precious metal casting. And so jewelers now have taken up SLA. And also, this is starting to find its way into foundry applications, into custom castings. And the way that casting is done is you take your printed components and this is put into a plaster mold, and you fire that mold, and then you're able to pour metal. So you burn out polymer, and you pour metal into the cavity to cast whatever component you're interested in. And so you can check out this application note. There's a lot of interesting stuff online out there, but this gives you now a little bit of idea of not only what you can 3D print directly, but what's possible with SLA technology, because the resolution is so high. So you can get really interesting cast detail or casting molds that you maybe couldn't get using conventional technology. Okay, that's the burnout schedule if you're interested in looking at that. Then finally, let me skip to this slide. And so what's going on in dental right now is trying to 3D print not only tools to think about dental devices, but directly printing dentures. And so there's a nice application note at Carbon about this. It turns out that there's lots of dentures out in the world. Dentures are also expensive, just like hearing aids are. So there's a real big market incentive for applications in these areas, such as dentures, hearing aids. Of course, if you've bought headphones lately, you know that they're expensive as well. And so you see a lot of these different technologies are high margin businesses, but they're also customized to individuals. And that's where 3D printing really shines. Okay, I think Zoom is still going here. Let me just check my Zoom on my computer and see if this gets better. Bear with me 1 second while I log in. Or maybe my computer's not to let me log in. Okay, well, we'll keep going. Again, if there's any issues with the lecture, just unmute yourself, or if it gets really bad, send me an email if I'm not broadcasting anymore, but we'll go on like this. So
I have another quick question.
Go ahead.
Are the parts that are 3D printed, like the dentures and the hearing aids, going to be more expensive than like other methods, since it's like, I don't know, just a different process?
So that is a very good question. Well, my broadcasting just died here. 1 sec. So that is a great question. And that's what these different markets are working on right now is, you know, if you make dentures, you already have a business in dentures. And so the question is, how can you make money doing 3D printing, or do you want to even do 3D printing? Does it fit within your business model? And so that's something that companies are working on right now. It turns out for hearing aids, the entire industry 10 years ago didn't print any hearing aids. And now more than 95% of hearing aids are 3D printed. And so the industry has decided that the speed with which that they can make these hearing aids and the fit that they're getting and the performance they're getting is actually better than the conventional manufacturing processes for hearing aids. And so there had to be some early adoption. there had to be some experimentation on this, but the whole industry has decided that hearing aid manufacturer, the way to go is additive manufacturing. And so they're not going backwards. Now, if you make airplanes, there are very few parts in an airplane that are additively manufactured. There are a couple, but the whole industry has not decided that the entire airplane is going to be 3D printed because the technology is not just ready yet. And so that's a case where there still needs to be a lot more research in terms of where are the benefits for 3D printing going to come for aerospace. Same with automotive. The industry is still trying to decide what can be 3D printed and what can't be. Now, for dentures, it turns out that the speed with which you can 3D print dentures, the service that you can provide people, getting them dentures quickly, even though they might be, and the cost of dentures currently, even though they might be a little bit more expensive, people will pay for more convenience, they'll pay for a better product. And so even though they might cost a little bit more, folks have started to adopt 3D printed dentures. Same with Invisalign. So if you have clear braces or Invisalign, those are all 3D printed. And so the industry has basically decided that 3D printing is the most efficient way to do that. And so I would say that it depends exactly on what your business model is. But in general, introduction of new technology costs a little bit more to begin with. But as the technology is used more and more, the cost comes down, and eventually people decide, or they figure out how to make the new technology more convenient, more cost effective, and better than the old technology. And then the whole industry starts to switch. And so there's a lot of models on technology adoption. There's a lot of models about how new technology has moved into the marketplace. And we'll talk about some of those in future lectures. But, the examples that we're seeing now might cost a little bit more, but at least the convenience and the performance of those parts is good enough where people are willing to pay a little bit more, and then the technology will get better and better.
Awesome, thank you.
Yeah, examples that we don't see are like 3D printed car tires, or 3D printed toothbrushes, or 3D printed plates and bowls. Those types of products are commodity. Everyone uses about the same thing. No one cares about customization. And we haven't been able to invent 3D printing process technology that's as good as the conventional processing technology. And so there's areas where 3D printing hasn't penetrated so far. And so that provides an opportunity, but also that gives us some examples. Let me work on this. That gives us some examples of where 3D printing might not be effective yet in order to start to change how people design and build products for that marketplace. All right, let me get the slides going here. All right, let's switch over. We've been talking about cyanate esters. I'm going to switch over to lecture 8.5. See if this comes up. There we go. That was nice. So we're going to talk a little bit more about SLA materials in the next couple of lectures. We're going to talk about different facets of SLA materials. So you'll have to stick with the chemistry for a little bit, but this is basically a preview of how these resins work, and hopefully will give you some different ideas about what you need to do to obtain the different sort of properties that we're going to talk about. So once you SLA a part, in general, you have some sort of post-processing. And in general, one of the first things you do is you rinse the part, because the part is coming out of a liquid photopolymerization vat. And so even carbon technology that's pulled out of the vat, there's still a lot of uncured resin on the surface. And so there's various ways to wash or rinse the part, and that's generally the first thing that's done. And we'll just talk a little bit about that. There isn't a lot of science developed in this area. It's mostly just rules of thumb. So after it's all rinsed, you remove the support, and we don't talk too much about supports in this class. That's covered in other 3D printing design classes and 3D printing manufacturing classes. But if you have supports, you physically clean up the part after all the uncured resin is rinsed. And then what we'll talk about a lot is curing the print. So you can either do this with photo curing, or thermal curing. And this is really that last step in the diagram that I showed at the beginning of class, where you get gelation in the 3D printing process because you need to form a solid part, but you really complete the network in the post-cure step. So you react any unreacted bonds that are in there. You try and get a full extent of reaction either by photo curing or thermal curing, depending on what the resin is. And so curing the print is one of the most important post-processing steps. And this is your driving cross-linking reaction to completion. So that's important, and it's important to think about this step because you can also over-cure and then your parts get too brittle, and then you have issues with that. But this is a key part of going from demonstration or general use resins to engineering resins. So for washing and curing, there's a lot on this, of course, online and a little bit in the literature, but this is in general just driven by rules of thumb. Solvents can be isopropyl alcohol, alcohol water mixtures. Green solvents are highly desirable, such as glycols. Acetone is not very good because it's flammable. And methanol is really bad because it's toxic, although some people use that. And so your life cycle of your part or the total cost of your part should include what solvents you're going to use, how often can you, or how long can you use them for, how much washing do you have to do. And so this can add cost and complexity to part production. And then how do you do the final curing? You can have slow natural light curing. That sometimes is fine for lab use, but if it's slow, that's an issue. Usually this is done in a UV chamber like we saw on the previous slide, or oftentimes it's done using thermal curing in an oven for a certain time and temperature, and we'll talk about that in a couple slides. So this washing and curing is often prescribed for whatever resin you buy. So if you're buying a resin from 3D Systems, they will tell you how to wash and cure the part. And so that's often part of how you get properties that are certified for that specific resin is you have to pay attention to the post-processing. So let's see if this comes back. If not, I'll try and share it from my other computer. One of those days today. Here, let me share my screen on my other computer, see if I can get this going here. All right, can you all see that?
Yes.
Okay, yeah, my iPad is not feeling it. Okay, So anyway, this washing and curing, like I said, is usually prescribed by the manufacturer of the resin, and you have to follow these washing and curing steps in order to get the properties that are of interest. And so, like I said, there's guides online for this, and this is just another example of clear resins that we've already talked about. So, cyanate esters are one of the newest types of 3D printing resins that are available, and they're really useful because they have properties that are similar to epoxies, and they have the ability to be both photocured using acrylates and then post thermally cured. So you can make liquid resins out of this chemistry, and then you can take those resins through SLA where you get gelation, and then finally you can do a thermal cure in order to get this cyanate ester cyclization reaction. So let me walk you through this. So the first thing that would happen, well, I can't draw on my screen now, but let me describe it to you, and we'll fill in the blanks if I can get my screen sharing working. But there we go. Let me try this. Okay, we're back. See if this works. Okay, there we are. So what's interesting, and this will get not fuzzy in a second. What's interesting is you can SLA the oligomers. So shown on the left-hand side of this slide are all small molecules for the most part, right? They're not cross-linked, they're floating around, and if you work on the chemistry just right, these can be liquids. And in the SLA process, we're not cross-linking the cyanate ester using photopolymerizations. We're going to do this thermally, but we put in some acrylates in the oligomers that undergo this acrylate photopolymerization. Then we can do the thermal cyanate ester polymerization. So the photo, nope, I can't write on this slide for some reason. Oh, let's see if this works or not. That was going so well this semester. Then the last couple of days, the internet is just, or maybe my iPad is just getting tired. But anyway, the point of that slide is, and it'll come back in a second, is that you do photo cross-linking of acrylates, and then you do thermal cross-linking of the cyanate ester. And the cyanate ester is what gives you the properties, whereas the green part just holds together with the acrylate so you can set the shape. And so if you look at a couple of Joe DeSimone's talks online, or if you look at a couple of the application notes from Carbon, they talk about using light to shape and then using post-processing to get the properties that you want. And that's the real magic of SLA. Oh, okay, this is not going to work. Let me go back to sharing. On the other computer. We'll get this sorted sooner or later. There we go. All right, good. So in this oligomer right here, so we have oligomers. Plus monomers. And we know this is going to be liquid. First, we're going to do UV photo of acrylates to get a solid. And then we're going to do thermal of cyanate ester to get the properties. So this is two reactions. One, UV cross-linking, and two, thermal cross-linking. This diagram is not perfect because in here, acrylate and methacrylates are part of the oligomers. So it's hard to show everything in this diagram, but this is the cyanate ester chemistry, and this is a really strong cross-linking agent, and so this is what gives really good properties, and we'll show some specific molecular examples in a second. And so the cyanate ester chemistry comes from this thing. This is a cyanate ester, and it makes this cyanurate right here, which is this funny looking 6-membered ring. So this is the crosslink. And it's just a little bit different organic chemistry than what you saw in the acrylate photopolymerization part. So if you're interested in the chemistry, there's lots of cool papers on this because this is actually pretty old chemistry. We've had cyanate ester cross-linking for a long time. It's just a little bit different than epoxies, but it's employed in similar applications to epoxies. And you see some properties here. So this specific material is sold by Dinsmore, and they sell it in carbon printers. And so this gives you an idea of what's needed for under the hood automotive applications, electrical enclosures, sort of high-end mechanical properties and thermal properties. And what's interesting is that this is yellow because of that cyanurate linkage. Well, and it looks a lot like Ultem polyimide. It actually has a lot of the same properties as Ultem polyimide. It's just not it's not a thermoplastic. So that's just an interesting aside. Let me get this back. But if you've never run into a cyanate ester, they're worth looking at because they have a lot of cool properties, and it turns out they're used a lot in industry, even though we don't get to see them because they're under the hood for automotive applications. But this has been a high value product for the 3D printing industry, and a lot of different companies have cyanate ester chemistry in their resins. So a lot of the high temperature resins that are thermally cured are based on this exact reaction that we just talked about, if this can come back. So the next slide, if you go to the next slide, you see a couple of patents there, and we're going to talk about the recipe that they use for this. Let me just, this is going to go poorly. So let me share my screen again. All right. So we just talked about this slide. And so this is from, these chemical structures are from these two patents, and I won't be able to draw on this slide, but I'll just talk you through it in the last few minutes here. So you see those OCN bonds, those are the same as what we saw in the previous slide right here. That's the cyanate ester, the OCN that's going to trimerize. Let's see if I can get my pointer going here. Well, let me just talk through it here. So you make an oligomer shown at the top that has these OCN bonds, but is also going to have some acrylates in it as well. And so that's where those R groups come from. And you notice this is a polymer, so you can put lots of different stuff in there. So you can start to get dual functional resins that have this UV photopolymerization character and then have a thermal cross-linking character as well. And this is from one of Carbon's patents. And so you can look up this patent. And so what they use is, again, this AeroSci 371, which is a cyanate ester, and it's just based on a Novolac backbone. You don't have to worry about that, but it has those same OCN groups attached to the backbone. And then they mix it with different acrylates. And so you see that Sardimer CNI 20Z, if I can read that, or CN120Z, whatever that is. And you see this triacrylate crosslinker, and they talk about the recipe that they use for their cyanate ester. And this is a patent example from Carbon. And so it gives you an idea of everything that goes into one of these resins. So they take their mixture of cyanate ester, so this Huntsman XU371, 2.5 grams of catalyst, and then they take 25 grams of this polyurethane-based diacrylate, and they basically mix this up and then print it. And it also gives you the washing and curing for getting the cyanate ester desired product. And then if you go on in the patent, it lists what the mechanical properties are. But you see now this is a multi-component mixture, and they also talk about this catalyst that's needed. So this zinc ACAC that's needed in order to get the cyclization of the cyanate ester. And that catalyst is put in there. That's the 1500 ppm of zinc 2 acetanoate. And that's really interesting because now you're putting in the precursors for different reactions after you do the UV photopolymerization. And when we talk about polymer-derived ceramics, and when we talk a little bit about ceramic printing, we'll bring this back up because they do exactly the same thing where they're taking a polymer and turning it into a ceramic by putting some catalyst in there and then doing pyrolysis rather than just this lower temperature curing. But if you're interested in really specific recipes for a lot of these SLA resins, you can find them in the patent literature, and the examples provide some nice formulations. The last slide that we'll talk about is flex materials. And what's cool in this paper, and this is where we'll pick up next time, is that by changing the ratio of this polyether methacrylate and this cross-linking methacrylate, you can get flexible materials of all different moduli. And so this goes back to the idea that all these stereolithography resins, you can obtain a wide range of properties just by changing the reaction mixture. And in this paper, they talk about getting hard and rigid materials with thousands of megapascal properties, all the way down to soft and rubber-like materials. And so we'll talk a little bit more about how to put together these resins, what properties are available, and how to get good properties out of SLA parts next time. And hopefully the internet will be cooperating a little bit better as we move on in SLA. Any questions or comments before we finish class? Okay, well, I will end the lecture now, and I will see you on Zoom on Thursday. Please take a look at your homework, and I'm happy to do office hours or answer any questions by email as you make some progress on those assignments. Thank you very much.